Absolutely. First thing, draw a picture. It's not a function, but that totally doesn't matter. What could you always do to make this easier to graph? What could you do? No, it equals x already, but what could you do to the right side of this if you wanted to? Yeah, so that's y times 1 minus y, correct? So where does the thing cross the y-axis? 0 and 1, correct. What kind of shape is this going to have? It's going to have a different orientation, but what type of shape is it? Parabola, facing which way? The side, that's not enough. I need left or right. It goes left? Does it go to the left or does it go to the right? How could you figure that out? What's the easiest way to figure out if it goes left or right? What? Plot a point. Don't figure out concavity. Don't, like, phone Einstein. Guys, plot a point. Seriously, plot a point. So how about when x, plot a y value, right? If you wanted to, right? Put a y value. How about a y value of 2? If you plug a y value of 2 in there, what's the output going to be? Negative 2 for x, right? So if you plug in 2 for y, so if you know if y is 2, if you know y is 2, x is going to be negative 2. So you know that it crosses right. Is that correct?
No, it's 2. Y equals 2.
Yes, this is y equals 2. This is y equals 2, and this is x equals negative 2. Oh, my scale. Sorry, I'm very sorry. Thank you. So it goes up there. So which way does it look like it points? To the left, exactly. So what's this thing going to look like? Looks like this. Everybody see that right there? Right? And where are you rotating? You're rotating it about the y-axis, and it's also bounded by x equals 0. What is x equals 0 also known as? No. The y-axis. X equals 0 is the y-axis. So what shape are we rotating? We're rotating that shape right there. We're rotating that shape right there. So if we rotate that around the y-axis, what is this thing going to look like? It does this. And then what do you draw after you draw the outline? One disk. So there is one disk right there. Is this a washer or a disk? It's a disk. That's correct. Are we integrating with respect to x or y? Y, because the slice is perpendicular to the y-axis. What's the lowermost limit of integration? It goes all the way up to 1. Exactly. It goes up to 1. We factored it. It easily found intercepts. And now you just need the radius squared, but it needs to be in terms of y. Do we already have it in terms of y? Yeah. Ready? Y minus y squared, and you put a pi on the outside.
So as long as we're integrating with respect to y, then it doesn't matter whether or not it's function relative to x.
Yes. No, it does. It has to be a function relative to y. Exactly. And but that being said, it might double back on itself for some crazy reason, and then you just integrate with you integrate in pieces. You have to look at yourself. Does the boundary change? Does what is defining the outer ridge change? This one doesn't. It's one function doing it the entire time. It's one function. It is this function the entire time. Can you define a piecewise boundary? Like, could it be this and then veer off into space the other direction? Sure. You know, like when you're spinning something on a lathe, like you could have a nice curve and then it could be bumpy. You know, you can definitely do that in this case. You just have a separate function. In this case, it's just one function. Can you integrate this? Say yes. This. It's going to look like this, right? And what do you end up with for a shape? So here is that's just poorly done. It's not really mirroring it too well. I'm doing my best here. It's a little too steep on that. I'll fix it. Like this. And I went over too far. So it goes to there and like this. There it is. It's a poor mirror image, but do you understand what I'm trying to draw here? So it's spinning. It's spinning around this axis right there. It's spinning around that axis. So you have to draw one of the slices. You draw one of the slices. So it's going to be here and here. So you have this. It's rotating around the x-axis. Do you see that now? Yeah. Okay. So is this a washer or a disk? It's a washer. Are we integrating with respect to x or y? X, because it's perpendicular to the y-axis. Exactly. What's the leftmost limit of integration? -1 to 1. Do you notice any symmetry about this one? Yeah, so instead of going from -1 to 1, we can go from 0 to 1, and what do we put out front? A 2. Is everybody okay with that? In this case, what's the bigger radius? What's the bigger radius? What's the upper function? Secant x, yeah. Secant x, exactly. What's the lower function? 1. Exactly, that's what you're punching out of it, right? So what do you integrate? It's 2 pi, 0 to 1 of secant squared minus 1 squared dx. Do you square this? No, that is the most common mistake on these. Do not square that. Does that look familiar? To your lack of knowledge. Here we go. Ready? D dx of sine x. What's that equal to? Cosine x. Good. D dx of cosine x. Sine x. Let's do d dx of tangent x. Wow, I got much less confident right here. This is the equivalent of knowing vowels, everybody. What is it? Secant squared x? Okay, as a class, we think it's that. Okay, good. We got Bill. Maddie, I think, had an answer there. What about d dx of cosecant x? What do you think it is? I gotta pause it. This is a train wreck. Washer, yeah, definitely a washer. So you draw this line. It's a disc with a hole in it. So it's this, right? There's one disc. You see it, everybody? Integrating with respect to x or y? X, because the slice is perpendicular to the x-axis. So it's going to be pi, big R squared minus little r squared. And do you square the entire quantity? No, you do not. What's the leftmost limit of integration? 0, and it goes to 1, exactly. The upper function, and now here's the thing. You have to be careful here, the radius, right? Sometimes you have to draw in the radius to really see it. This right here is the first radius. That's the big radius right there. This is the big radius, right? Because you have to go from the axis of rotation to the outer boundary. So what is big R in this case? 1 minus x cubed, right? And what's little r going to be equal to? Root x. Do you see how to do it now?
Yeah.
You see it now? So you take these and you substitute it in there, and then you do the integration. We're good? Okay. It ends up getting thinner, right? But for the first 2, so all the way up to here, to 2, it stays the same, right? And then the boundary changes. Do you see how the boundary changes? So how many integrals do you need to do? 2. So if we were going to do this, we were going to do pi, the integral from 0 to 2. Are we integrating with respect to x or y? Y. What's the outer radius? 4 squared, right? What's the inner radius? 2 squared. So that's the first one, correct? And then the second one is pi 2 to 4. What's the outer radius stay? 4. And what do you subtract? Close. Y squared, because it's in terms of y, remember, right? Okay, so that's not impossible. But how many integrals is it? 2. Is there another way to slice this up, to slice this rotational solid up so that you can integrate it with one integral? Yes, there is. In 6.3, they talked to you about what? What's the word before it? Cylindrical. Did I spell that right? C-Y-L-L-I-N. There's only one L. So what we did before, what we were doing before was taking a rotational solid and slicing it perpendicular to its axis of rotation. Instead, we're going to rotate something, and we're going to think of it as a blade. Imagine we had a really sharp piece of metal, and we bent it into a tube, and then we cut it down, and then made the thing a little smaller and cut it down again. You're going to slice it, and you're going to get a lot of concentric shells. You're going to get a lot of concentric shells. So what you're going to get on this one is the following picture. We're taking those cylinders, and we're unrolling them. So do you see the cylinder right here? Everybody sees it. If you cut it right there, it's going to spring out, and what are you going to be left with? This sheet that has a thickness of dx, your height, and here's your circumference, which is 2 pi r. So if you did this, you could think of it as springing out, and you just have these cross sections where the width, the length of these things just tends to be the circumference. So go ahead, yeah.
So what we're doing is we're
Equal to right here. We're hope that when we do this, it comes out to equal the same thing as those. Let's try it and see what happens. So we have 2 pi, the integral, oh, what's the integral of x squared? 1/3 x cubed from 2 to 4. So we have 2 pi over 3 times 4 cubed minus 2 cubed, which is 2 pi over 3 times 64 minus what? 8. So that's going to be 56 times 2 pi over 3. Is that nicely divisible? No, it's not, right? So you can just say it's 112 over 3 pi. So that was pretty doable, right? So what do we hope this is equal to? We hope it's equal to what we did on top, right? Let's actually do it and see. Is Mr. Seamon perfect? No. Do I like talking about myself in the third person sometimes? Not really, actually, so I don't know what I'm doing. Okay. Okay, so let's try this. The first one's pretty nice, isn't it? Let's do that one. Actually, we'll just take this one and put it up here. Okay, so let's do this one. So what do we end up with? Pi integral from 0 to 2 of 12 dy. That's correct, right? Did I do that? I make those mistakes. So we end up with pi 12x from 0 to 2. Oh, y. Thank you. And you end up with, plug in 0, you get, so it's just going to be 24 pi. Is that correct? Okay. That's bigger than that yet? No, so at least we're underneath that value, right? At least we haven't surpassed it, and we're adding things together, so it's good. So far, I'm feeling okay. So let's keep going here. So we have pi times 16y minus what? 1/3 y cubed from 2 to 4. So you have pi times 64 minus 1/3 of 64, right? Minus 32 minus 1/3 of 8. Is that correct? So pi times, what's one? Ugh, I don't want to do this. You see, but do you understand how this is fundamentally different than what we just did? So hopefully we come out to be the same thing. So I am not failing as a teacher today, but I'm really setting myself up there by saying that. So we have 32 minus 1/3 times 72. Do you see how I got that? No, it's not one. It's 1/3 times 56, right? Look, 64 minus 32 is 32. I have negative 1/3 times 64 and positive 1/3 times negative 1/3 times 8. What's 64? Oh, it is 72. What is 64 plus 8? Are you okay with what I did right there?
Yeah.
Good. I need help sometimes. What's 1/3 of 72? 24? Oh, because it's negative and you're adding, so it's 56. Thank you. Okay, so we end up with pi times 3, so it's going to be 96 minus 56 over 3. So what is that equal to? 40 over 3 pi. So what did we get here? We have these two things. So we have 24 pi. I don't know why I'm putting that in a box. Sometimes I just go with it. Plus 40 over 3 pi. So what's that equal to? 72 over 3 pi plus 40. Is that correct? We end up with 112 pi over 3. Now, we did this one pretty clean, and did we end up with the exact same thing? Absolutely. Is this do you guys buy into the fact that sometimes this is going to be easier? Yeah. You just need to visualize it in your head and say, oh, wait, this is one integral. This is one integral. This is one integral. Excellent.